Hi there, folks. Today we're going to talk about metamorphism and metamorphic rocks. Um, as I probably said when we did the lab, or will say when we do the lab, I don't do a whole lot with metamorphic rocks in this class. Traditionally, when we go over the rock cycle and we mention that metamorphic rocks are created by exposure to extreme temperatures and or pressures, I didn't go much farther than that. Well, not too long ago, I decided I'd better expand my lecture just a little bit. And so this is a fairly new PowerPoint. If I stammer through something or act a little surprised, it's because, well, I've only given it once before. So here we have a lovely rock hammer, well worn, well used, well loved by the looks of it. But more importantly, this rock hammer is lying on top of a lovely piece of gneiss. And we know it's nice because, well, it's a very nice rock, isn't it? Yeah, that joke is pretty old. We know it's a gneiss because of the banding, the layering, the black and white striping. As I tell you in lab, it doesn't have to be black and white. It could be any color. But boy, when you see striping like that, you could almost guarantee that it is a gneiss. I'm a little distraught that my letters are cut off here. Hopefully that does not continue to be an issue. So, what is metamorphism? Metamorphism is a process wherein mineralogical and or textural changes happen in a rock due to exposure to extreme pressures and or temperatures. You're getting tired of that and or, I apologize, but it can be just mineralogical changes due to temperature. That should technically be backwards here. Mineralogical changes due to temperature, or textural changes due to temperature and pressure. Doesn't matter which order these are in here. There we go. So what I'm saying is you can get exposure to high temperatures without getting high pressures, but once you're getting exposure to high pressures, you're definitely getting the temperature. So that's where the and comes in. No, I had that right the first time. I had that right the first time. Crying out loud. So it was temperatures. Yeah. Sorry, folks. Trust yourself, right? Isn't that what they always say? Just like on those multiple choice tests. Pressure and temperature, or just temperature. Yeah, I don't like it that way either. But either way, okay. Oh, we got the thing where they light up each time. Lovely. Okay, so what causes metamorphism? As we've said a number of times already, changes in temperature and changes in pressure. This doesn't happen at the surface, folks. Yeah, there we go. These rocks have to get drawn inside of the earth, okay? And that's where they get exposed to high temperatures. It's not laying out in the sun. We look at the nice little wedge of the earth here, and we see that the core of the earth is 9,000 degrees Fahrenheit, termed geothermal gradient. You've heard that word before. Tells us, generally speaking, that as we go into the earth, what temperature increase we can expect to see. Now, there is something that you'll see at some point in here. Well, here we go. That occasionally we could bring the hot stuff up much closer to the surface. Okay, hot spots, igneous intrusions, and basically what happens here is that, well, as the name implies, intrusions. This magma is intruding much higher up into the surface of the earth than it should be. And we've got a great example here, Yellowstone, If you're familiar with Yellowstone National Park, you know that they've got all kinds of hot water features going on there, from geysers to mud pots and whatnot. That is because very, very close to the surface there is a giant pool of magma heating up all the groundwater there. Okay, you may recognize the term caldera here if you've had some volcano studies already, and depends when we're doing this in the semester. Sometimes I've talked about volcanoes, sometimes I haven't. A caldera, you know, is a collapsed volcano. So you know that we're implying then that this was Yellowstone National Park was once a giant volcano and blew itself to smithereens, collapsed down into it, and well, there's still magma underneath there. Okay, so back to the point at any rate. You have to bring the rocks into the earth to experience the high temperatures, or occasionally, okay, the high temperatures can come closer to the surface. Well, how about the pressure then? Again, inside the earth, all right. Burial pressure, what we call lithostatic. Lith means rock. Static, as in stasis, means constant. So constant rock pressure is what lithostatic pressure means. And that's just the weight of all the material above you. If you ever think back to playing football in your backyard or something like that, and you get tackled by 3 or 4 people and you feel the weight or the pressure of them above you, that would be, you know, people static pressure. It's the same idea. But imagine enough pressure to actually cause some changes in your body, enough weight or mass above you. The other way to cause pressure is through tectonics, plate tectonics. All right, 2 continents smashing into one another. Huge, huge, huge pressures, and that certainly can bend rocks. We call it differential because it is varying in direction. So here's some examples of lithostatic. All right, and directional, as I said, sorry, frog in my throat there, and directional stress, as I said earlier, with the differential, it's pointing in a particular direction. Delta T, delta P, all right? In chem, I think I stole this from chem class. It might work in physics too. The triangle here, the delta sign, stands for changes in, okay? So mineralogical changes come from changes in temperature, and textural changes come from changes in pressure. And remember what I said a few slides back? It was kind of garbled because I was moving the words around there. You can get mineralogical changes without getting textural changes. All right, but it doesn't work vice versa. So, mineralogical changes. We see this with a couple different ways. If there's only one mineral present in the rock, you see that the grains just get bigger. Okay, sandstone turns into quartzite, and we get these basically an obscuring, really, of the mineral grains. What used to be sand grains now turns into a much more cohesive rock, and that's because those grains grew bigger and grew together. Same thing when we go from a limestone perhaps to a marble. Marble, oftentimes you can see the grains, okay, but the same idea is happening here. Now, multiple minerals present, that gets a little more complicated, and you can, well, this topic can actually go on for an entire semester, believe it or not, metamorphism. So we'll just leave it at that. If there's multiple minerals present, it definitely gets a little more complicated. Not our concern right now, though. So here we go. I just talked about sandstone to quartzite, one of the common metamorphic transitions. Okay, now, as we were just talking about increase in grain size and texture, depending on how much attention you paid to igneous, sorry, but I mean, if you, depends how in depth you got when we talked about igneous, you might remember that when we talked about going from coarse grained to fine grained, that we had those filed under textural changes. So it might have been confusing for you a slide or two back when we talked about increasing grain size under mineralogical changes, but not textural. You follow me? All right. In metamorphic rocks, these are completely different kinds of geologists, and unfortunately, that's something that happens when you blur everything about geology into 14 weeks. These are completely different kinds of geologists. Metamorphic petrologist. A petrologist is someone who studies rocks, right? So a metamorphic petrologist versus an igneous petrologist, and they don't really care what the other person uses for their vocabulary. Sometimes they share words for different reasons. So in metamorphism, we could change grain size without changing texture. But once you start moving the minerals around, that's what they mean in metamorphic geology. That's what they mean by textural changes. And the word they use is foliation. Okay, foliation is an orientation of the mineral grains. It's an organization. It really is. It should be in the direction of the stress. Remember, we showed somebody pushing on, I believe it was a deck of cards, one of the previous slides, and that's the direction of the stress. That's the direction the mineral grains should move. I want to see if I don't. Okay, so the way I typically describe this in lab, and you heard it in the lab cast, or we'll hear it in the lab cast. For me, playing cards comes to mind. Okay, whatever card games you play, euchre or rummy or gin or whatever. Everybody throws their hand in at the end of the round. And if you're like me and you're not a very good shuffler, you have to do a couple things in order to shuffle. First thing I do is take my hands and squeeze all the cards in from the left and the right and from the top and the bottom. And I don't do it very gracefully, but I'm applying pressure from the left and the right to bring all the cards together that way. And then I'm applying pressure from the top and the bottom. I'm doing it on the table in front of me as we speak here, so if you hear that little scratchy noise, that's me. Top and the bottom. Okay, and then you do that, a much more refined version of it in your hand, so all the cards are nice and neat and in order again. That's stress foliating the cards. In this case, we're using it to put the cards back to order. Okay, but oftentimes the stressor or the pressure could be used to push something out of order. So we're back to this gneiss. Okay, a gneiss is a foliated rock. It's one of a handful of foliated rocks that you'll learn. As we said, not all rocks have textural changes. Not all metamorphic rocks have textural changes. In lab, you learn that's the foliateds and the non-foliateds. Remember, the non-foliateds were only affected by temperature. The foliateds were affected by temperature and pressure. So anyhow, picture of a gneiss, and this is what they mean by movement of mineral grains. So, nice segue for us here. I must have planned that. All right. When we talk about metamorphism, we talk about low grade versus high grade. Okay, and this is where we kind of blend with lab a little bit here. Some of the rocks you'll learn are slate, schist, and gneiss. There's also a phyllite in there as well. Slate, phyllite, schist, gneiss. I don't know why I opted to leave phyllite out of here, but those can also be used as adjectives, descriptors. Slaty, schisty, gneissic. So the rocks are defined by particular textures, and I don't want to steal too much from lab. You'll get to recognize what those rocks look like in lab. But that ties right up with this low to high grade metamorphism. Slate is on the low end, gneiss is on the higher end. And the more we move through this process, we call it a straight line metamorphism. I have a picture for this? I do. All right. The more we move through this, the more deformation, the more changes we see. I guess I dropped phyllite out of this because it wasn't in this picture for some strange reason. You have a piece of phyllite in lab. It's basically wavy slate. I like phyllite. So what we see here, we always say that we can start with one rock, okay? Slate comes from a shale, typically, shale or a mudstone. So we start with a piece of mudstone, a sedimentary rock, and we apply just a little bit of heat to it, and it turns into what we call a slate. All right. Then as we slowly increase the temperature, we start to increase the pressure. And I'm completely ignoring blue schist over here, by the way. We don't even talk about blue schist. We go from a slate to a schist to a gneiss. All right. And gneiss is as far as it can go. Gneissic texture is, well, remember the rock cycle? What comes after metamorphism? What comes after metamorphism is remelting, okay? And that's where this gets kind of cool, is you got to picture this rock down there being deformed and all the stuff that's going on around it. In my mind, by the time it gets to a gneiss, in order for those minerals to move all around like that and all the stuff that's going on there, I picture it almost like a water balloon, okay? There's this very thin skin on the outside of it that represents where that rock ended. But on the inside, boy, it's just a jumbled mess. It probably isn't quite that fluid at all, but in my mind, to keep it, to make this process make sense, that's what I've always thought of. Please don't worry about the different kinds of forces. As I said, we really just are grazing over what metamorphism is. Okay, protolith. Protolith, you're much more likely to hear me say as a parent rock. Okay, what was the rock before it was a metamorphic rock? I've mentioned a couple already. Sandstone turns into quartzite. Sandstone is the protolith. Quartzite is the metamorphic rock that it turns into. Limestone to marble. Limestone is the parent rock. Marble is the metamorphic rock. Shale to slate. Shale is the protolith or parent rock. Slate is the metamorphic equivalent. Okay? When it comes to the rock test, this is what you'll be asked for. Okay? In the third column, we mentioned the third column of the rock test in lab class. Not only will you have to tell me granite igneous or limestone sedimentary or marble metamorphic. Okay, that's probably what you expected. It's just like the mineral test, a name and a group, right? But the rock test has a third column, and that third column is further classification. Back to my point. For metamorphics, it's parent rock. So you would have to say marble is metamorphic, and then you would tell me it's parent rock of limestone in the third column. So pay attention to parent rocks with your metamorphics. And speaking of which, with the foliateds, with your gneiss, your schist, your phyllite, and your slate, okay, the parent rock is always the rock before it. Phyllite would go right here. So the parent rock for gneiss is schist. The parent rock for schist is not here right now. It is phyllite. The parent rock for phyllite is slate. And the parent rock for slate would be shale or mudstone. Okay, anywho, you'll get that in lab, but since we're here, I figured we'd talk about it. And it was right there because I knew we'd want to talk about it. There we go. So, for non-foliated rocks, okay, we just did most of these. Oh, the only one we didn't do is right here, anthracite coal. What other type of coal do you know? Yep, exactly. All right, bituminous coal. So for your non-foliateds, we keep it simple. We've got all sedimentary rocks for the protolith or the parent rock. Okay, if you missed it earlier. You got shale, limestone, sandstone, bituminous coal. Alrighty, folks. I paused there for a moment. I want to move on to the last part here, talking about something called contact metamorphism. If you recall, a couple minutes ago I mentioned that most times you have to bring the rock to the hot, but sometimes you could bring the hot to the rock when magma intrudes into the surrounding rock. One second. Okay, sorry again. I don't know if you guys notice the pauses or not, so I keep saying sorry every time I pause. So contact metamorphism. What happens is the Earth is old; she's cracked and whatnot, and magma, like everything else on the planet, follows the path of least resistance. So if it moves anywhere near the surface and there's cracks in the rock, it will intrude into those cracks. It'll pressure itself, squeeze itself right into those cracks. And what happens then is that magma is so hot that it affects the rock around that crack. We call that a bake zone. Okay, I compare it a lot to a bonfire. Okay, you've all hopefully been around a bonfire, and you know that the closer you get to it, the hotter it is. If you get too close, you put your shoes up on the rim there and fall asleep, you might find that your bottoms of your sneakers have melted away or something like that. And as you move farther back, you find your comfort zone. Well, the same is true with these intrusions, except the rock can't go anywhere, of course. So the rock right surrounding the intrusion receives the most amount of heat, and then as we move farther and farther away from it, we see less and less temperature effects. Well, remember, temperature is one of our effectors for creating metamorphic rocks. Temperature creates non-foliated metamorphic rocks. So what we see then is when magma comes up into the crust, it can create some low-grade metamorphic rocks in the area called the bake zone.